We've got some fresh images of 3IATLAS, a third ever interstellar object observed.
We've got some fresh images of 3IATLAS, a third ever interstellar object observed from Earth. We expect comets and asteroids to follow the rules of physics. But every once in a while, something breaks those rules. That's what's happening with 3IATLAS, the third interstellar object ever discovered, and maybe the strangest yet. Webb's instruments picked up a pulsing glow, signals in sync, and movements that suggest more than chance. Could we be watching the first evidence of something alive or even engineered drifting toward us? Join us as we uncover why 3IATLAS has become the object no scientist can ignore. Webb Telescope sees the impossible. When the James Webb Space Telescope was aimed at 3IATLAS in early August, the results were not at all what scientists expected. Webb's infrared instruments are designed to pick up heat, the faint warmth of distant stars, galaxies, and cold rocks drifting in space. Normally, a small interstellar object like this would appear as little more than a dim smudge reflecting what little sunlight it could catch. But the data from 3IATLAS told a very different story. Instead of a diffuse glow or scattered radiation, Webb recorded a sharp, concentrated point of light right at the object's center. Even more puzzling, the emission was holding steady at a level nearly 3 times brighter than any computer model predicted. No dips and fluctuations, just a clean, unwavering output. For astronomers used to studying comets, this was deeply unsettling. A comet's brightness usually flickers as it spins, venting gas in uneven bursts. Some parts of the surface warm faster than others, releasing plumes of vapor that scatter sunlight in irregular patterns. But here, nothing of the sort was happening. The light from 3IATLAS was smooth and constant, like a lamp switched on in the darkness. Webb's team checked and rechecked the instruments. Could it be a glitch? A calibration error, interference from the sun or from Earth? The logs came back clean. The readings were genuine. The heat wasn't just on the surface. It seemed to be radiating from deep inside. Something that no ordinary rock or ice ball should be able to do at such a distance. The first images showed no signs of the classic cometary tail, no stream of dust trailing behind it, no visible coma spreading out around it. Instead, the object seemed tightly wrapped in its own glow, like a sealed ember drifting through space. Astronomers at ground-based observatories began to compare notes, and the picture was the same across the board. This wasn't just unusual, it was unprecedented. One of the senior instrument scientists on the Webb team described it as a beacon in the dark. Not because it was signaling, but because of the way it burned so cleanly and steadily. Natural objects don't usually behave with that kind of stability. Stars do, power sources do, but comets almost never. The community quickly realized they were staring at something they couldn't categorize. If the brightness wasn't caused by sunlight or surface activity, what else could it be? Was it internal heating from radioactive elements? Was it trapped energy somehow escaping through the core? Or was this something far stranger? Something that didn't fit into any of the usual boxes? For the moment, the Webb team stopped short of drawing conclusions. What they could say with confidence was simple. 3IATLAS was shining far brighter than it should in a way no one had ever seen before. The universe had handed scientists a puzzle and Webb had provided the first undeniable piece, a rhythm that shouldn't exist. When scientists dug deeper into the James Webb Telescope's observations of 3IATLAS, they noticed something that immediately stood out. The light from the object wasn't just bright. It had a rhythm. The brightness rose and fell with striking precision, repeating every 4 hours. It wasn't random. It wasn't chaotic. It was steady like clockwork. In nature, most space objects don't behave this way. Comets flare when gas escapes from cracks in their surface, but those flares are uneven, unpredictable, and messy. Asteroids tumble, reflecting sunlight at odd angles. Even stars, though they sometimes pulse, usually do so with irregular timing, influenced by their size and structure. 3IATLAS, on the other hand, kept glowing in a pattern so regular that astronomers could set their watches by it. The Webb team began plotting the intervals, comparing the cycle against the object's rotation and orbit. If the brightness came from surface features, the timing should have shifted as the object turned. But the 4-hour pulse remained locked in place, unaffected by its spin or its changing position relative to the sun. That meant the source of the glow wasn't external. It was buried deep inside. To researchers, this was one of the most troubling details. Natural heat sources tend to vary. If radioactive material was driving the glow, the release would be gradual, not sharply timed. If sunlight was somehow triggering it, the cycle would match the daylight rotation of the object. But here, nothing lined up. The heat seemed to rise and fall on its own schedule. With no outside cause, some scientists compared it to a heartbeat, not because it implied life, but because of its regularity. Others described it as a metronome in space ticking away in silence. What everyone agreed on was that no known comet or asteroid had ever been recorded showing this kind of behavior. The discovery sparked intense debate. Was this a natural process no one had ever documented before? Could there be an exotic mechanism, something involving trapped energy or strange chemistry that might account for such precision? Or was the regular pulse pointing to something more deliberate? A system built to function this way? For the team working with Webb's instruments, the priority was caution. They checked the timing against every possible source of error. Instrument cycles, software artifacts, even the telescope's own orbital movement. But the pulse held firm, independent of the equipment. The data was clean. By now, the discussion had moved far beyond routine astronomy. A repeating signal with no natural explanation raised possibilities that many scientists were hesitant to voice. Still, the evidence was undeniable. 3IATLAS was not only shining too brightly, it was glowing with an internal rhythm that shouldn't exist in nature. The signal nobody expected. After the strange 4-hour glow pattern was uncovered, researchers around the world turned their attention to 3IATLAS with a different set of tools, radio telescopes. These instruments don't capture light. They listen for radio waves, faint signals that often travel across the cosmos. Normally, astronomers use them to study galaxies, pulsars, and the static of the universe itself. But when they aimed their dishes at this visitor, they found something no one expected. The first hints came from the Allen Telescope Array in California. While sifting through the data, scientists noticed a narrow band signal that rose above the background noise. It wasn't strong, but it repeated at regular intervals every 4 hours, the exact same rhythm that Webb had already seen in the thermal data. This was no coincidence. The light and the radio waves were pulsing in sync. Independent teams in South Africa and Europe quickly joined in using their own facilities. They confirmed the same signal. This ruled out the possibility of local interference like radio chatter from satellites or Earth-based equipment. The pulse was genuinely coming from the direction of 3IATLAS, far beyond the reach of any human-made source. What made the signal even more unusual was its stability. In space, natural radio bursts from stars, gas clouds, or magnetized objects usually vary in strength or scatter across a wide band of frequencies. This one stayed locked on a narrow frequency range, repeating with remarkable precision. That kind of order is rarely, if ever, seen in natural systems. Over several nights, the pulse showed another surprising trait. It shifted ever so slightly in response to the solar wind. Space weather carried by streams of charged particles from the sun seemed to nudge the signal. It wasn't random drift. The change lined up with real-time measurements of solar activity, as though the source of the transmission was somehow aware of its environment and adjusting along with it. For astronomers, this was a turning point, a steady repeating radio pulse synchronized with a heat cycle and tuned tightly to a single band. The list of natural explanations was shrinking fast. The discussion turned from whether the signal was real to what could possibly be creating it. Still, scientists remained careful. Radio telescopes have a long history of picking up mysterious signals that later turned out to be satellites, interference, or even equipment faults. But with independent observatories across different continents all detecting the same thing, those everyday explanations no longer held weight. The discovery fueled both excitement and unease. On one hand, this was the kind of data astronomers dream of. A mystery unlike anything in the catalogs. On the other, the implications were unsettling. Objects drifting through space don't usually behave like transmitters. Yet, here was 3IATLAS broadcasting a rhythm in lockstep with its internal glow. For the first time, the possibility could no longer be ignored. This interstellar traveler might not just be reflecting energy, it might be sending it. The flare and the turn. By mid-August, the mystery of 3IATLAS took a dramatic turn. Observatories tracking the interstellar object were recording steady readings when, without warning, its brightness spiked. In less than an hour, the glow jumped by nearly 40. No comet or asteroid had ever been seen changing that quickly. Then just as suddenly, the surge leveled off. Not back to its old state, but to a new, brighter baseline. At first, astronomers thought they might be looking at a normal outburst. Comets often vent gas when pockets of ice break apart, releasing sudden jets of vapor. But those events usually leave signatures. Flickering light, uneven sprays, or visible dust streaming away. None of that appeared here. Instead, the flare looked smooth, almost controlled, as if something inside had simply increased its power. While teams worked to explain the jump in brightness, another surprise emerged. Orbital calculations, which had been consistent for months, no longer matched reality. Using precise tracking from multiple telescopes, analysts discovered that 3IATLAS had shifted course. Its path bent closer to the plane of the solar system. A subtle but unmistakable deviation. The timing caught everyone's attention. The flare and the change in trajectory occurred almost together, logged within the same observation window. For experienced orbital modelers, this was unsettling. Comets do change direction when jets of gas push against them, but those movements are irregular and don't line up so cleanly with changes in brightness. Here, the data suggested that the object's shift wasn't random. It was tied to the sudden burst of energy. The European Space Ace Near-Earth Object team ran simulations using different assumptions. They tested whether hidden outgassing could account for the push or whether the estimates of the object's mass might be off. None of the models fit the observations. The change was too neat, too direct, and too consistent with the flare itself. For the first time, some researchers began to consider a possibility they had avoided. What if the course change wasn't accidental at all? What if 3IATLAS had maneuvered? The idea was met with caution, even discomfort. Spacecraft we design here on Earth adjust their paths by burning fuel or using solar sails. But no natural rock drifting in from another star should have that ability. And yet the evidence was stacking up. A sudden increase in brightness followed by a clear alteration in trajectory. Both linked in time. As reports circulated through the scientific community, the tone shifted from curiosity to quiet alarm. If the object was steering itself, then its path wasn't entirely governed by gravity and sunlight. That meant its arrival was not just a matter of chance. From that point forward, 3IATLAS was no longer treated as just another interstellar visitor. It had become something else entirely. An object whose movement suggested intent. Alien chemistry in the data. As 3IATLAS drew closer, astronomers turned to one of the most powerful tools available, spectroscopy. This technique breaks light into its components, creating a fingerprint that reveals what an object is made of. Every element and compound leaves its own unique mark, allowing scientists to study composition even from millions of miles away. When the first spectroscopic data came back, there were no surprises at first glance. Familiar signs of water ice, carbon dioxide, and simple molecules showed up. The usual ingredients of a comet. But layered on top of these common markers were features that stopped the analysts cold. Several absorption lines didn't match anything in existing catalogs. These were signals that didn't belong to ordinary space rocks. As the data was processed, strange peaks appeared that hinted at metals usually locked deep inside planets, not drifting in icy bodies. There were traces resembling rare earth elements, materials that on Earth are central to electronics, magnets, and advanced technology. Digging deeper, researchers spotted patterns that pointed to alloys, mixtures of metals fused together in ways nature rarely produces on its own. These weren't the simple blends formed in meteorite collisions or stellar explosions. They carried the hallmarks of refinement as if shaped with purpose. Most striking of all were features echoing the properties of so-called quantum materials, substances that exist in theory and experimental labs, but have never been seen naturally in space. These materials interact with energy in unusual ways, making them candidates for futuristic technologies. Finding even hints of them in the spectrum of 3IATLAS was beyond unexpected. It was almost unsettling. At this stage, the scientists had to be careful. Could these signals be the result of interference? A trick of overlapping data? Teams checked and rechecked. Independent observatories around the world ran their own analyses. The same odd fingerprints appeared again and again. Whatever was in 3IATLAS, it wasn't just ice and dust. For the research group studying the results, the conclusion was difficult to ignore. The mixture of rare earth elements, unusual alloys, and materials with properties bordering on the engineered didn't look like random cosmic chemistry. The spectrum suggested something assembled, not simply formed in the chaotic churn of stars and comets. This raised unsettling questions. If 3IATLAS carried metals and compounds beyond natural explanation, how did they get there? Was this the shattered remains of some larger structure? Was it coated or reinforced by processes no one yet understood? Or was it evidence that the object itself was never a comet at all, but something designed for a purpose? By late August, access to the raw data was already being restricted. New security protocols went into place, and discussion of the unusual spectral lines moved into closed channels. Outside the research community, the public heard little more than rumors. Inside, the weight of the discovery was clear. 3IATLAS was not just bright. It was not just pulsing or shifting course. Now the chemistry itself was pointing in a new direction toward design. First Contact Protocol. By late August, the mystery of 3IATLAS had reached a breaking point. The object was too bright, too steady, pulsing with a rhythm, broadcasting a radio signal, and even altering its path. Each new piece of evidence left fewer natural explanations on the table. Behind closed doors, the discussion began to shift. If this wasn't a comet or an asteroid, then what was it? That's when a bold decision was made. Instead of just observing, scientists decided to reach out. NASA, working with the European Space Agency, drafted a simple test, the kind used for decades by the Search for Extraterrestrial Intelligence or SETI. The message would not be words or images, but math and physics, the most universal language we know. The transmission carried prime numbers, the sequence of digits that can't be divided into smaller parts. It also included basic constants, the kind that defined the rules of nature, like the ratio of a circle or the structure of the periodic table. Nothing fancy, nothing complex, just a signal that any intelligent mind might recognize as intentional. The message was broadcast in a narrow band aimed directly at 3IATLAS. And then the waiting began. Days passed in silence. But exactly 72 hours after the transmission went out, the radio arrays lit up again. A reply had arrived. It wasn't strong. And it wasn't clear. The signal was distorted, stretched by its long journey through space. But buried in the noise was a pattern that lined up with the transmission window to the second. The pulse matched the timing of the outgoing message. It was not random static. It was a response. The room where the data was first reviewed fell silent. For the scientists who had spent their careers searching the skies for faint hints of intelligence, this was the moment they had imagined but never expected to see. A signal sent out and a signal returned. From that point, everything changed. The discovery was no longer just about astronomy. It was about security, communication, and the future of human contact with something beyond Earth. Agencies began restricting access to the raw data. Internal memos shifted from open collaboration to classified channels. The debate was no longer about whether the anomalies were real, but what humanity should do next. Was the reply simply an acknowledgement, a reflection of our own message, bounced back in a cosmic mirror, or was it the first deliberate exchange with something aware of us? No one could say for sure. The only fact that could not be denied was this. A signal had gone out into space and something near 3IATLAS had answered for the scientists who had tracked the object since its discovery. This was both thrilling and unsettling. A mystery rock from another star system had turned into the first potential conversation with an intelligence beyond Earth. The green shift. In September 2025, observers noticed 3IATLAS glowing green, a shift first captured during a lunar eclipse in Namibia. Scientists suspect gases like cyanide or possibly dicarbon, which glow green under sunlight, are being released as the object heats up. The change hints at chemical reactions within the comet's core or surface layers, exposing new materials never seen before. While cyanide has been confirmed, dicarbon remains uncertain, leaving the exact cause debated. This sudden color shift could be a crucial clue, tying into the object's other anomalies and helping reveal whether 3IATLAS is natural or something far stranger. A debate with no answers. As summer turned to fall, the growing list of discoveries surrounding 3IATLAS forced the world's leading astronomers into an emergency session of the International Astronomical Union. These meetings are usually quiet affairs focused on technical definitions and small refinements in data. This time, the atmosphere was different. Everyone understood that the object approaching our solar system was rewriting the rules and it demanded answers. The task was straightforward in theory. Test every natural explanation that could account for what had been observed. Teams were assigned to evaluate the most likely scenarios, drawing on decades of comet and asteroid research. If the anomalies could be explained by known physics, then the mystery could be contained. The first model on the table was outgassing, the standard process that makes comets brighten as they vent frozen gases. But that theory collapsed under the numbers. The glow of 3IATLAS was too steady, too concentrated, and far stronger than sunlight at its distance could trigger. No jets of vapor were seen, no debris trails, no messy plume of dust. The second possibility was radioactive heating. Some celestial bodies generate internal warmth as unstable elements decay. Could this be the hidden engine? The calculations said no. Radioactive decay produces a slow, uneven release of energy, not a repeating cycle with perfect timing. It also couldn't explain the sudden flare or the synchronized radio pulse. Another idea was dust scattering. Perhaps fine grains around the object were reflecting more light than expected, giving the illusion of extra brightness. But the spectral data showed a focused core of heat, not a diffuse halo. Dust explains hazy comas and long tails. What Webb saw was something entirely different. A pinpoint glow, as if centered deep within. Then came the check for human error. Were the instruments faulty? Were the data corrupted by background noise or calibration slips? Teams dug through logs, compared independent telescopes, and matched observations across continents. Every test confirmed the same result. The readings were real. One by one, the models fell. Outgassing, radioactive decay, dust scattering, even simple miscalculation. None could explain the complete chain of evidence. The brightness, the steady rhythm, the sudden flare, the course change, the unusual chemistry, and now the repeating signal. The pieces refused to fit into any natural category. The debate stretched for hours. Some participants argued for caution, insisting that undiscovered processes might still be hiding behind the data. Others admitted that the evidence looked engineered, though no one wanted to say the word artificial out loud. The session ended without consensus, but with one undeniable conclusion. The known explanations had been exhausted. For the scientific community, this was a rare and unsettling moment. Astronomers are trained to search for patterns in nature, to find order in the chaos of space. But with 3IATLAS, the patterns they were seeing did not match any catalogue. What remained was a question no one had the tools to answer. The universe had presented them with an object that did not fit. Countdown to encounter. As September 2025 draws to a close, 3IATLAS is no longer a distant curiosity. It is now on approach, moving steadily toward the inner solar system. For months, it has been studied through numbers, spectra, and signals. But soon, for the first time, humanity will get a direct close-range look. Its path recalculated again and again shows it will pass within range of Earth's most advanced observatories. Ground-based telescopes, orbiting satellites, and even instruments on the far side of the Moon are being readied for the event. The hope is simple: to capture as much data as possible during the brief window when this object comes close enough for detailed imaging. Unlike ordinary comets which often pass without much notice, 3IATLAS has become the focus of a coordinated global effort. NASA, the European Space Agency, and independent observatories have synchronized their schedules, pointing every major instrument toward the predicted corridor. Even telescopes normally reserved for deep sky surveys have shifted to track this single visitor.